Okay, so the random experiment, for the sake of recording, let me repeat. We are trying to prove a lower bound of k squared over polylog k for R3k. The random experiment, we pick the n, which is some small constant times the target lower bound. And the random experiment is straightforward. Each edge is given red or green independently, but the red has a probability p, while green has probability 1 minus p. P is likely to be very small because red triangles are more likely to come, and we want their probability to be small. So P will be much smaller than half. 1 minus P will be much larger than half. In fact, P will be very close to 0 and 1 minus P will be very close to 1. The bad events, we have categorized it into 2 red triangles and green KLs. The probability of a red triangle is P cube, all the 3 edges being color red. Green KL is 1 minus P to the power number of edges in an L click, which is L choose. Okay. K click, K choose 2. Okay, at some point I think I have made a confusion between K and L. Okay, since I think going forward it is all yeah, good. Okay. Yeah, since going forward it is all L, let me upfront say that both our K and L are the same. Okay, otherwise I might have to keep switching here and there. Okay, and then the dependency is what we should analyze a bit carefully. So here is everybody clear how this dependency table comes up? So the first entry here is the number of type 1 events on which a single another type 1 event can depend on. Okay. So here, first of all, there is a complication in the way we speak, because it's not about depend on, because it is actually mutually independent to the complement. But that is fine. But is it clear how we get this 3 times n minus 2? This 3, this is a critical point. We will keep using this in almost every Lowash local lemma proof. Okay, this finding the dependency graph. Okay, so here 3 is the number of edges in the K3. The type events is having a red K3. And now, in order for another triangle to have any interference with this triangle, because we are coloring are on edges, the vertices do not play a role here. So the other triangle should also share at least one edge, which means the 2 vertices for the triangle is already has to be from within the vertices of the given triangle, and the remaining vertex has n minus 2 choices. Okay. Similarly, let's say the second row first entry. Okay, this entry. How does it come about? This is number of triangles which can influence a L click. So for a triangle to influence an L click, you should pick at least one edge from the L click. There are L choose 2 of them, and the remaining one vertex of the triangle you can pick from any of the remaining n minus 2 vertices. So in particular, this will have triangles which are inside the L click, right? Because it's only an n minus 2 there, not n minus L. So, this one triangle could be a subgraph of the KL, then that's surely a dependency, right? So in fact, it's a very strong dependency. So we should remember that also. So that's the idea of this dependency. And then this upper bounding each term in the dependency table is something which we are all sure about. And now the Lowash local lemma V3. Right? In Lowash local lemma, using V3, first of all, remembering the version V3 itself is a minor challenge. But the key challenge, the most difficult challenge, is to figure out this xi and xi, because it looks like it is coming from nowhere. It is not directly a probability. In some sense, it's a scaling of the probability, so that when you scale it down into a inside of sub events condition, if you condition it some dependency many times, you still have a large enough that conditioned value is still more than the probability. So it's easy to kind of talk something about xi like that, but figuring out xi is usually difficult. Okay, but now we know that we have to, in order to apply LLV3, we have to satisfy these two inequalities. Okay, and yeah, but before getting to this inequality, we always have to use the symmetry of the problem to reduce the number of unknowns. We have one xi value for each of these events. Okay, and there are n choose 3 plus n choose l total number of events. So picking them different xi values would be impossible to track at least. And but more than that, here there are only two types of event. So it's kind of natural to expect that we only need two xi values, one for the type 1 event, which we will denote by x, and the other for the type 2 event, which we will denote by y. Then this expression now reduces to something which involves only 4 unknowns, right? Okay, 5 variables, n, l, p, x, and y. N is already known. In fact, L is also known if the question is posed like, show that this is a lower bound. Okay? Then this is the L that we are, this is the N that we are looking for this K or this cell. Now, if you rearrange the terms, you can write either N in terms of K or K in terms of L. So between this N and L, we can solve, one in terms of the other. So in this case, since your N is, what we are trying to do is L over log L squared. If you rearrange again this, log L and log N, whenever there is a polynomial dependency, you should know that, whenever what I'm saying is that if some alpha to the power some K1 is given to be equal to some beta to the power K2, where K1 and K2 are both integers, then K1 log alpha is equal to K2 log beta. So when you are comparing logs, they are within constants of each other. Okay, log alpha is equal to theta of log beta. So that is why here, this is root 10. This would actually L would be root 10 log L if I take this to the other side. But log L and log N are of the same order. Okay, that is why I can write it as root 10 log N also. These constants will take care of whatever is the approximation error that we are introducing. Okay. So then we solve for P. This is a very a very rough reasoning because we are claiming that we are at least thinking that anyway this Lowash local lemma is not going to help much with type 2 events because their dependency is almost as high as all the events in the graph, and hence we want kind of a union bound to apply there, and so on and so forth. We solve for P, and Y is in the next guess, which we go by again, the same idea. Your Y is something which can make this term a constant. Okay. So from this, from this point onward, you should. So to make this a constant, you can lower bound 1 minus y by 4 to the power minus y, so that you'll get something like 4 to the power minus y. So if you choose y times n choose L to be much less than 1, then this is almost like 1 by 4 or even better. A lower bound of 1 by 4 or even better. And then you solve for x based on the next inequality, and you are done. Okay, that's finishing the analysis. I think I'm kind of getting, I'm repeating too much, so I don't think there is much of a reason to go through. But one point I wanted to highlight was, if we could have solved this using LLLV2, we would have done that, right? But then why did we not use LLLV2 and to get the same bound, why did we go for LLLV3? So for LLLV2, what we want is that the probabilities summed over all the dependency set. For each I, you figure out all the events on which AI can depend. You sum the probability. It has to be upper bounded by 1/4. This will not be true. This is possible to do for type 1 events dependency events, right? But because for a type 1 event, if your I is of type 1, then the dependencies include 3n, in fact 3 times n minus 2, which we upper bound by 3n, 3n other type 1 events, which will give you union bound addition, or sorry, not union bound. This addition will give you 3n times p cube, and the number of type 2 events on which it may depend on is 3 times n minus 2, choose L minus 2, 1 minus. So from this, actually, it is possible, if you simplify this, it is possible to identify a P and in fact, here you only need to identify a P, because unlike the B3, you don't have these extra unknowns X and Y. You can actually identify a P to satisfy this inequality. But the problem occurs in the type 2 expression, where this guy kind of really dominates, right? What is the L that we are targeting? We are targeting an L which is of the order n raised to 1 by 2, right? We are targeting an L which is of the order root n log n. Yeah. So this is, we're targeting an L which is of the order of root n log n. So your L choose to is going to be in order something like n log squared, and I'm ignoring all the constants. So L choose to times n is order of n squared log squared n, and we want this times p cube to be much less than 1. So because everything total should be added up to 1 by 4. So this term itself has to be less than 1 by 4. In particular, approximately, I'll say much less than 1. But what does this tell about p cube? N squared, correct. This says that p cube has to be much less than 1 by n squared log squared n, and if p is that low, then this guy here is going to be difficult, right? What is 1 minus p? This is approximately e to the power minus p. L choose 2 is again around not n squared, it's around n polylog n, right? N log n. So with this p, you will get e to the power minus, yeah, this is a p cube. So I should put 1/3 when I'm talking about n squared. Okay, let me ignore the logins for now. N by 2 by 3. So this is n to the power minus 2 by 3 into n, which is n e to the power minus n to, okay, whether I should have used 4 since I want a lower bound for all these guys. Okay, so this is 4 to the power, yeah, even this lower bound, yeah, because p is between, it's not even between 0 and half. Okay, so I cannot use lower bound. Sorry for the confusion. Okay, something approximately this. But the main point is that this will be an e raised to n to the power 1/3. N to the power of positive quantity increases with n. So this n to the power 1/3 goes to infinity as n goes to infinity, which means this goes to 0. No, what am I? N raised to minus 2 by 3, n raised to 1 by 3. It goes to infinity. So this is 4 power, yeah, this you can even upper bound by a e raised to, or was I wrong? When I was trying to do this, I was thinking this will not work. E to the power minus n to the 1/3 is, can be, that's quite good enough, right? Did I make any mistake in the calculation? Because at least when I was trying to use LLLV2 here, something was not working out. N log n, correct? N squared log squared n p cube. P, yeah, this 2 by 3 is correct. P is of the order of n to the power 1 by n to the power 2/3. This is L choose 2. Okay, this is still going to be some n into n square, but I should be able to kill it with this 1 minus p, e raised to minus p into L choose 2. L choose 2 is again order n only. E raised to minus p, p is into the power minus 2 by 3. There is an n there. So you should have got an n to the power 1/3 minus of n to the power 1/3 in the denominator. That was sufficient to kill it. No, but I'm surely making a mistake because I know that at least Alon and Spencer uses the third version of Lowash local lemma. So what mistake am I doing? L is root n log n. Correct, root n log n. Yes. I think I was overlooking this guy. This is n minus 2 choose L minus 2, right? So yeah, like let us say this together is approximately n choose L. I mean, there is n minus 2 and all. So this is approximately n to the power L, which is some constant e to the power L log n, which is again something like e to the power root n log n. Okay, whereas this e to the power minus p n log n, again log n's I'm not being careful about, so if I make a mistake there, don't bother. This is something like n to the power 1/3, right? So this root n dominates this n to the power 1/3. So this n to the power half minus n to the power 1/3 is a positive quantity. So this goes to infinity as n tends to infinity. Okay, so actually I should have said these two together are conflicting enough constraints so that if you make p too large, this guy will go above 1/4. If you make p too small, this guy will go, this second guy will go above 1/4. And this is a case where unfortunately there is no sweet spot in between where you can find a p that will simultaneously make both of them less than 1/4. Okay, so this is where a coarse approximation of the Lowash local lemma, even in its V2 form, does not work. Okay, yeah, 25 minutes. So so please go through this Ramsey lower bound things very carefully. It's a good exercise to for this understanding the Lowash local. Okay, so this we assume is done. Yeah, the second question I'll wait for answers from you. Right. So first let us try this. Okay, who wants to attend this bound?
I will attend.
Yes, Francis. So we'll start with the random experiment.
Yes. Coloring the vertex, each vertex.
Color each vertex independently and uniformly at random with how many colors?
K colors.
With K colors. Okay. Yeah. Now next step.
So we have to identify the bad event.
Yeah. Correct.
Let A be the event. That VA has at least one color among the 1, 2, 3, etc. K colors.
but this is not the end of it, right?
Yes, yes. Appears.
Correct.
At least beta plus 1 times.
Very good. Very good. This is the bad one, right? Because this is what a beta frugal coloring should not permit. No color should appear more than beta times in the neighborhood of any vertex. So what Francis has just told us is the negation of that. There exists, or at least negation of that for a particular vertex Vi. Okay, that it's in its neighborhood, there is at least one color which appears more than allowed, which is more than beta number of times. Okay, very good. Now we have to do the calculations.
Beta plus 1 times in neighborhood of Vi.
It appears in this n of Vi is a shorthand for neighborhood of Vi. Okay. Now the probability calculations.
Okay, so you draw one vertex Vi and neighbors.
Okay. So you have this Vi and you have its neighbors. U1 to maybe U delta, right? Delta is given in the question.
Yes, maximum degree is delta.
Delta,
so
yeah. At most U1 to U delta.
Yes.
Okay.
So for so among the delta, at most delta plus 1 delta neighbors, so we can pick the same color by delta choose P plus 1 choices.
So this is the number of B plus 1 subsized subsets of n of this n of Ui, right? N of Vi.
Yes.
Your n of Vi is nothing but U1 to U delta. So what you are saying here, this delta choose B plus 1 is the number of beta plus 1 sized subset
of the same color. Same color.
Oh, of the same color. Okay, this is the number of possible subsets of size beta plus 1 among the neighborhoods.
Yes. And for each the same color will appear 1 by choice will be 1 by K.
Yeah, so this can be monochromatic in K ways, but I did not understand your last sentence. Can you say that again? When you
so suppose C1, C2, C1 is the color that should be appear. So that for the color C1 should appear, will have a probability 1 by K.
In one vertex of this chosen set or all vertices of the chosen set?
For one vertex, it's 1 by K.
One vertex, it is 1 by K, right? That I agree.
So for all the vertex, it's 1 by K power beta plus 1.
Yeah. So for all vertices in a set S, subset of n of B with cardinality of S is equal to beta plus 1, to get color some Ci is 1 by K to the power beta plus 1.
Beta. Yes. So for P of A will be so delta choose beta plus 1.
Correct.
Into 1 by K beta plus 1 into K.
So that is a key point.
Yes.
Why? Because now you are not talking about any particular color. Yeah, when you are only thinking one color should appear in beta plus 1 vertices, it could be any of the K colors. So yeah, in my mind, I actually calculated this together. I would have written like, what is the probability that this beta plus 1 set gets the same color? It would be K by K to the power beta plus 1.
Okay.
Right? Yeah. So this I can just simplify and write K to the power minus beta. K 1 by K to the power beta. But I also want this, what will you put here? Is this an equality or is it something else?
It's at most, sir.
This is an at most. What? Because why? Because these, beta plus 1 sized sets here, they may have overlaps. Right. So we are using a Ewing bound, and hence we will only get the upper bound. In fact, this is the number of events or number of subsets.
Yes.
Right. And then this is the probability that one such subset has the same color. Okay. So this is done. Okay. P of AI is less than this. Okay. Now what is the next step?
So dependency.
Yeah. So we'll analyze the dependence. So what is the dependency degree? How many events can one of this depend on?
It's a neighborhood of Vi and Vj is disjoint. So.
Exactly. So if Vi and let's say Vj does not share any common neighbor, then remember that this event is only about, in fact, this event has nothing to do with Vi. This event is only about coloring some beta plus 1 subset of n of Vi. So, and this is, any event here is about Vj, right? So, if Vi and Vj are independent, distance at least 2, distance at least 3, which means their neighborhoods don't overlap, then it is independent, okay? Or I can say that the event AI is mutually independent to which set? To the set of events Aj such that n of Bj intersection n of Vi is empty. Okay. So, but this will mean what is the size of the dependency? The Di's size, how can we upper bound?
So at most delta plus delta into delta minus 1.
Correct. So what Francis is doing is, like, you think about a vertex V. This is delta and this is delta into delta minus 1. Okay. I would have actually not included this.
Okay.
Right. Because let us say, just for the sake of argument, it's not, even if you include this, nothing bad will happen, because this will also reduce to delta squared only, right?
Yes, sir.
This is also delta squared minus delta plus delta. This will also be delta squared. But just for, let's say this is Vi and Vj, they have an edge between them. But suppose there is no triangle containing both Vi and Vj, which means this neighborhood is disjoint from this neighborhood, then actually they are independent. But we don't have to use that kind of strict analysis when it comes to this. Okay, so this is the D that we are talking about. So we are almost there. Yeah. So now the last step is to apply the lemma, right?
Apply the lowest.
Yeah. Which is, in this case, I think V0, V0, because E comes in. Whenever in the question you see an E, you should think about applying V0, which would mean we want something like EP D plus 1 less than or less than equal to 1, I forgot. So here E is E, P we have an upper bound, that's enough, which is delta choose beta plus 1 times k to the power minus beta. Yeah, and this D plus 1, actually if you did not have this delta, even this D plus 1 you could have upper bounded by delta square, but what did I? Yeah, so that is why you have this delta times delta minus 1. I should have put in actually a plus 1 there anyway. So this is delta times delta minus 1 plus 1 is less than or equal to 1. And that is almost, I forgot this plus 1, but this is almost exactly as it is given in the question. Right? So this is done. Okay, very good. So that's done. Who wants to try the second version with this bound? The blue one. Priyanka, do you want to give this a try? Did you get time to look into this?
No, sir.
That's okay. Suman, what about you?
No, sir.
Hmm.
I did the first one, but first one is also incorrect. I
Okay,
didn't try.
okay. Vishnu, did you get time to look at the blue bound? Could you attend this?
Sir, I tried only first one. Sir.
Okay, first one you had got?
Sir, not completely, but I stuck on a table. Sir. I couldn't approximate exactly.
Yeah, so actually, yeah, that is, whenever you're thinking about a slightly complicated application of this Lowash local lemma, or even the previous guys, there are always two challenges. The basic method is also a challenge, but then there is a lot of these approximations that we have to do. Okay, so in fact, that is in order to help that part only. These expressions are actually ugly, but they are ugly. Them being ugly is to your advantage, because this clearly tells what is the P and D that you are looking for in the Lowash local. Okay, so yeah, but that's okay. You can try. Who else had made an attempt?
Sir, for the blue one, like I'm thinking like looking at beta size subsets of the neighborhood.
Exactly. So here, let me highlight what would be P. Right, so your P is just going to be this much. Okay, I think the entire rest of this guy is going to come from the dependency graph. Okay, so here what Abraham said is correct. I'll say the intuition. So this is part B. Part B, the random experiment remains the same. Right, this is the same, where each vertex is given colored 1 to k uniformly at random, but the bad events you analyze is different. Okay, so when Francis was analyzing, he started with this BI and a beta plus 1 sized subset of it getting a monochromatic color, okay, or getting the same color, right? So you got only how many events? The number of events for Francis was only n, because there is one bad event per vertex. Okay, whenever you are thinking about, sorry. Sorry. Whenever we are thinking about using Lowash local lemma, if you really do not care if the total number of events blow up, right? You are only worried about the dependency. Okay, so the reason that why I gave these two bounds for the same problem is to drive home this point. Okay, so you have to sit back and understand this. When your choice of the bad events, choice of the experiments will also sometimes be dictated by the technique that you plan to use. If you are going to use union bound, then you should not blowing up the number of events is against you. But if you are planning to use the Lowash local lemma, the number of events is almost a don't care for you. What you should be worried about is the dependency, which means smaller and smaller events are going to give you better results. Okay, so here one vertex having k plus 1 vertex, k plus 1 neighbors with the same color is still a complicated event. What could be a simpler choice for bad event is what Abraham just said. This is something like, I'll again index it with some, I do not even know what to index it. I'll just call it AJ, not that, or AI, it doesn't mean anything. It means, okay, that name is tricky for me. So let me call S1, S2, etc. some SM, the collection of beta plus 1 sized subsets. Okay, so this I will call this some beta plus 1 sized subsets of vertices, all of which share a common neighbor. Okay, or let me write it also once formally. S is equal to all those, the script S is equal to all those subsets of B of G. What are the conditions? The size of that is beta plus 1, but with this extra condition is that there exists some vertex B in B of G such that this entire set is in its neighborhood. Okay. So again, what would be approximately the size of this collection? So this would be the total number of bad events in your system. How many can there be? It is at least upper bounded by n times delta choose beta plus 1, right? Because I can also count it from the vertex side. For each vertex will contribute around delta times beta plus 1 to it. Some of them may get cancelled out, because if two vertices like B1 and B2 share beta plus 1 or more neighbors, then some of these guys might be counted twice. That's why I'm discounting that. Okay, so this is a number which is much larger than it. So the total number of events has really gone up, which might be worrying for somebody who is trying to use the union bound. Okay, so Abraham, I agree with the choice of the bad event, but now the next step would be to analyze the probability of the bad event, right? Yeah, but this is only the collection. The bad event is that the bad event is the S is monochromatic.
Why is it n times? Like we may count the same set again and again in terms of different vertices.
Huh. No. Like in a how do you say? The common case would be very few vertices have too many common neighbors. Like let us say this was a triangle-free graph. Okay, triangle-free will not help you. Suppose not many vertices had a lot of common neighbors. Then how many bad events can you, or how many such subsets can you make? You are restricted to picking the set from within the neighborhood of a vertex. That restricts your choice to delta times beta plus 1, but you can go and do that for any vertex. Is it okay, or Lijo, did I not understand your doubt clearly?
Yes, sir. I was my doubt was like, will we be considering same set more than once?
We need not. In fact, we will not. That is why this is only an upper bound. And by the way, this is not needed for the proof. I was only trying to drive home the point that even if the number of bad events, total number of bad events blow up, it should not worry us if you are planning to use the local one.
Okay.
Right? Yeah. Yeah. So the bad event is that one of these is monochromatic. Hence, Abraham, probability of AS would be again your 1 by k to the power beta plus 1 times k. So this is the easy part, right? Abraham, you are in agreement with me, right?
Yes, sir.
Yeah. Okay. So now I'll ask you this is 3.
I didn't fully work
This
this
where-
idea. I just got recently.
Okay. Yeah.
So this delta into delta choose beta was what made me think of this. So like when you're looking at a like I was thinking like the dependency, like you start from a vertex and then you go to its delta neighbors, and then from there you're choosing beta from its neighbors. That's how you get a beta plus 1 subset.
Correct.
That is dependent on this.
Yeah, but the only point you missed is that since now your event is also a beta plus 1 sized subset, there would be some in the particular event AS itself, there are beta plus 1 vertices. So you'll have to repeat this for all of them.
Yes, sir.
Right? Those are the guys on which you will depend on. Okay. Or in other words, I think your dependency will be if your dependency will be to the subsets of your kind of, this kind of second neighborhood. But again, saying second neighborhood is wrong. That's why I was stuck with this, yeah. But this is the picture, okay? So if you have a AS, which is a beta plus one set, the other events that can potentially influence this guy's, whether this guy is monochromatic or not, would be those events. Yeah, we will need, since actually there's a cleaner way to see it. I only have to check whether this AS intersection AT is equal to MT, right? Because our coloring is independently on vertices. So if two beta plus one sets have non-empty intersection, they are mutually independent. So how many other beta plus one sets can have a intersection with this? So you have this beta plus one sized set. Now, if somebody else have to take this vertex, then that beta plus one set has to be from one of the, this day there has to be one of the neighbors of that. And then from the, actually you have to include this vertex and then pick beta other vertices, okay? Those are the sets that will contain this guy, okay? So first you have to pick a neighbor of this vertex X, and then from the neighborhood of its neighbor, which is an N of B, you have to pick beta other vertices. So this choice of B, you have how many? So you have beta plus one choices for X. X could be any of these times. There can be delta choices for B, and then a delta, in fact, a delta minus one, because already X is one neighbor. Among the other vertices, you have delta minus one choose B. Okay, so the dependency is at most this beta plus one, delta, and delta minus one choose beta. Right? So this, if you now plug in back, actually now I think I can, yeah. So this is the P that we already have found out, and this is precisely what I just told, right? Beta plus one choices for X, delta choices for its neighbor. I could have written here delta minus one choose beta, but then I needed a plus one and so on. So delta choose beta less than. Okay, so this is in fact this will be a better one. Okay, what are common? This E and this E are common. Delta choose beta plus one and this delta choose beta is also kind of common. K minus beta is common. So what essentially compares is this delta minus one with beta plus one, right? So this beta is going to be much less than delta in cases of interest, right? Because you would never have, any coloring will be delta plus one frugal. So you are interested mostly when beta is much smaller than delta. So this bound is more easily satisfied than this bound. Since this is a hypothesis, satisfying it more easily is what you want. Okay, so this gives an improvement. Okay, very good. So yeah, now the next question is again a combination of these two, but I don't think we will be able to finish it here. So this is exactly the second bound that we are talking about. So let me give a brief attack route for this. I may not get time to finish it off. I should not have spent too much time on the Ramsey lower bound. Okay, so here the random experiment is the same as above. Right, but bad events are of two types. type 1 is like a, beta plus 1 sized subset of ND for some B being monochromatic. And type 2, what would be type 2 events? So easy to guess.
Monochromatic edges.
Correct. This is because of this, right? Okay. Type 2 events are monochromatic edges. So here the probability is easy to calculate. So P of some type 2, one event of type 2. Okay, some A of type 2 is 1 by K. Okay, K times K squared, 1 by K. Here, probability of some type 1 bad event we already had calculated. This is K power minus beta. This is K power minus 1. Okay, so this is K power minus beta versus K power minus 1. And yeah, now the dependencies, if you calculate T1, T2, T1, T2. So this type 1 to type 1 dependency we have already calculated in the previous question. This is the answer, right? Beta plus 1 times delta choose beta. Yes, yeah, delta minus 1 choose beta. It's okay. Delta choose beta. How many type 2 events can a type 1 event depend on? So that means an edge should share one vertex at least with this beta plus 1 vertices, right? That is the idea. This is the type 2 event. This is the type 1 event. This is a vertex coloring. In order for them to have any influence on each other, they should at least share one vertex, right? Which means this T2 edge is going to be of this form, right? So each vertex is delta edges at most. So there are beta plus 1 vertices in your type 1 event. So this will be the upper bound. Okay, now type 2 are edges. Okay, how many other? So now this is an edge. How many other beta plus 1 events can it depend on? Right. So that means at least this guy has to. One of these guys has to go into that beta event. In which beta events can it go? If you have your edge E here, this guy, the role of this B here can be any of its neighbors, delta of them at most, and then each of them has to choose delta minus 1 choose beta others. Right? So here it's just this beta plus 1 changes to 2. 2 times delta, and again delta choose B or delta minus 1 choose B to be more precise. T2 to T2 are 2 edges which share a vertex, which will be at most 2 delta. Right? From each edge, either this or this 2 delta. Okay. So is this clear or did I go really fast?
Clear.
It's okay. Okay. Now I can upper bound these guys. Just what is beta plus 1, and this is something like delta to the power beta plus 1. This is okay. Beta plus 1 delta. This is around 2 delta to the power beta plus 1. This is 2 delta. Okay, easy upper bounds, and now we have to use LLL last step. This is the dependency. Yeah, this was third step, the dependency, and the fourth step is to check LLL V2, which means we have to bound 2 kinds of things to. So for type 1 events, what would be sigma over this dependency of P of A? This will be the number of type 1 events it depends on is beta plus 1 delta to the power beta plus 1 times the probability of type 1 event, which is k to the power minus beta Yeah, plus for the type 2, the dependency is beta plus 1 delta k to the power minus. Okay. Now remember that when you look at these two rows, this row is kind of the dominating guy. So if you can, like, I'm assuming beta is at least 1, right? So this guy dominates the bottom row. So in fact, for the type 2, checking the premises of low-Wash local lemma is going to be easy. It's in fact a beta factor, beta by 2 factor below this. Okay? So this is the tough guy. But here also, in order to keep this guesswork minimal, we are also given some conditions which we can use. One is that delta has a lower bound and k also has this bound. So now it's only about substituting these guys. Okay, so delta so we have to show that this is less than 1 by 4, but delta is given a lower bound and k is given 16 to the power delta plus 1 by beta. Yeah, I had one, but I forgot. It was 1 week earlier, right? Delta k beta plus 1 delta to the power beta plus 1. This is 16 delta to the power 16 delta to the 1 plus 1 by beta. Yeah. And this whole to the power minus beta. So here this minus beta plus 1. Yeah, so this is some 16. Okay, as constants I should have known by now, but delta to the power beta plus 1. And here this will be delta to the power minus beta minus 1. Minus beta, correct, minus 1. So this goes off. Delta to the power 0 plus this beta plus 1 delta 16 delta to the power 1 minus beta. Okay, by the way, this second term, it is easy to see, right? There is a delta in the numerator and there is a delta plus delta to the power something more than 1 in the denominator. So this guy will surely go to 0 and this guy cancels out. But now you have a 16 power minus beta trying to attack a beta plus 1. That's a sure gain. This 16 power minus beta will win. Okay, but you have to substitute and see. I mean, in fact, that particular choice of the lower bound of delta, you can convert it into an upper bound for beta and maybe substitute that. That would be the way to go. But yeah, it's 9:59. So let me stop this now. Those who have another class can go now. But if anybody has any pending doubt, if you have any clarification, I can be around for some more time. So please feel free to ask.